Morning, everyone. It's my pleasure to introduce today's keynote speaker, Professor Yueng from Bangor University. Yueng's research covers physical processes that impact the climate in the polar oceans. She works in both the Arctic and the Arctic, and today she's going to be talking to us about mixing processes in the Arctic Ocean. Over to you.
Thank you. Thank you very much, Rob, and thank you everyone for making it this morning after what I hear was a raucous music event last night. But that, of course, makes me recognize that from our previous speaker, clearly the Challenger Society meeting is a meeting of rock stars in oceanography. So thank you to the organizers for inviting me to speak to my fellow rock stars, and I guess let's get started. Okay. So, mixing in the Arctic Ocean and beyond, hopefully this talk will appeal to many of you. It's not just about the physical oceanography, but the ways in which the Arctic Ocean and Arctic Ocean mixing are really important in climate. So why are we really interested in mixing in the ocean, for instance? Well, let's start with the sea ice. We know that the Arctic is one of the regions that's changing most swiftly and most rapidly in its response to climate change. We know that Arctic sea ice extent has really declined, and here we've got, let's go back. And here we've got the volume, and this figure here shows you how the volume of sea ice has really declined in the last 30 years or so, at the same time at which we are seeing Arctic amplification, where surface temperatures in the Arctic are rising at 4 times the rate of global surface temperatures. And the reason for that, of course, and the reason why this is so important to climate, is because of the ice albedo effect that many of you are familiar with. Sea ice and ice on the planet is white and reflects about 85% of solar radiation. And if you take that away from the ocean, then you're left with this dark ocean, which only reflects about 7%, instead storing that extra heat and changing the energy budget of our planet. So losing the ice obviously is going to have a positive feedback, and I don't mean that in a good way, on climate change. The ice and its kind of processes, and here is a schematic originally drawn for the Antarctic, but the same sorts of things do happen in the Arctic. We do get sea ice formation, and during sea ice formation, the fresh water in the seawater is what freezes, rejecting the salt content or the brine, which then creates cold, high salinity waters at its base. And despite what some of the AMOC community think, the Arctic is implicated in some of the overturning of AMOC, which of course most of us recognize to be an important, shall we go back? An important component of the Earth climate system. There is a recent paper, in case you want to read more about the Arctic's contribution to the lower limb of AMOC from Dipanjan Day, that's just appeared in Nature Comms. I did not have time to incorporate it in this new in this talk, but it came out 2 weeks ago, and it shows that about 30% of the lower limb of AMOC coming through the subpolar North Atlantic on the eastern side is from Arctic source waters. Now, how does this matter to you on your kind of lifetime? You know, it's all very well talking about big climate processes that happen on kind of slow timescales, but actually in our day-to-day existence, we do experience some of the impacts of this sea ice loss, in the sense that what we have here is one of numerous studies that are really interested in how to explain the correlation between sea ice loss in the Barents and Kara Seas. The outline here is Siberia and Norway over here on the left. And so you have sea ice loss in the Barents and Kara Seas to the north, correlated with cold winters in both Europe, that's where we are, and Siberia. And how does this happen? And one of the potential stratospheric pathways for this is that they postulate that sea ice loss enhances ocean to atmosphere heat fluxes. Makes sense, right? No ice preventing the heat loss from the ocean to the atmosphere in winter. And as a result, this then tends to reduce the north-south temperature gradients in the atmosphere, which in turn strengthens both the the low over the Arctic and the high pressure system over Siberia. And this high pressure system then draws down all these cold currents from the north over both Siberia and Northern Europe. So this is one way in which what happens to the sea ice in the north really does matter to you and I today. Now, the sea ice itself, of course, has also been a really greatly valued platform itself for science. And at the Challenger Society, we recognize the value of these original voyages by various explorers. And here we have the voyage of Nansen with the Fram, in which they intended to cross the North Pole by freezing their ship into the ice and waiting for the transpolar drift to carry them across the North Pole. It's all very exciting because they didn't get far enough north. At about 80-something, he decided, okay, I'm just going to get out, Norwegian Sea, get out and ski to the North Pole. And so he gets out with two buddies, and they try to ski to the North Pole, and at some point they decide, okay, we'll dive, we keep going, so let's turn back and ski back to the Franz Josef Islands, which is what they do. And eventually the Fram comes out of the pack ice a year later. So it's all very exciting. You want to go and read about that. It's The Farthest North. Is the book that he wrote about his voyage. But we also have Nansen to thank for reversing thermometers and Nansen bottles in which they took really important ocean observations that showed that the Arctic, unlike the mid-latitudes, is what we would call an upside-down ocean, in which there is a cold, fresh layer sitting above warmer seawater below. And so now you can start to see why we're interested in ocean mixing with respect to this ice. But apart from Nansen's voyage, various more modern researchers have tried to use the ice in different ways. The Sheba expeditions in the late 1990s were really important in delivering breakthroughs on Arctic cloud dynamics, atmosphere ice ocean fluxes, and the radiative balance of this polar region. More recently, the N-Ice project was the Norwegian Yueng sea ice cruise, and they drifted here. In this area here, they also froze themselves into the pack ice and drifted around kind of the Fram Strait area and did kind of overwintering studies of various ocean processes, looking at under ice productivity and open ocean storms. And then, of course, the much more ambitious Mosaic expedition, which happened in 2019 to 2020. This is a multidisciplinary, huge international effort that had lots and lots of people from atmospheric sciences who actually drove the thing forward, in which they froze the polar stern into the ice sheet and were also attempting to drift relatively like Nansen across the North Pole. They didn't get that far, and they had to drive the ship around a few times to find ice to refreeze into the pack, but eventually they did do this rather remarkable experiment, results of which we're still seeing coming out today. So the ice has been really important for science for a number of reasons, and I'm going to then tell you just what we know about Arctic Ocean mixing and the insights that mainly I've received alongside with my colleagues on the Peanuts project. This was one of the Changing Arctic Ocean projects, and our project was primary productivity driven by escalating Arctic nutrient fluxes. So we were really motivated by pictures such as these. This is a NPP, net primary productivity prediction from a model, and this really shows that in most, certainly marginal areas, in marginal shelf seas of the Arctic and the slopes, we're going to get enhanced primary productivity in the future. This is borne up by current satellite measurements, sea surface chlorophyll measurements from Kevin Arrigo and team as well. And so these predictions all show that the productivity is higher than you would expect from just losing the sea ice alone. Losing sea ice, of course, means more light in the ocean, able to drive primary productivity. But something else is bolstering the primary productivity. And so we postulated that it's obviously going to be ocean mixing, drawing deep nutrients up into the euphotic zone. And so we wanted to make some measurements, and we wanted to look at ecosystem responses using models and satellite measurements. This, of course, is the team. It was led by myself and my buddies Tom, Marcus, Joe Hopkins at NOC, and Neil Bannis at Strathclyde, and we had a whole host of talented postdocs and students alongside us. Now, an important addition to this figure here that I've drawn on are the warm water inflows from the Atlantic and the Pacific. So you have in red, the Atlantic inflow circumnavigating the deep basins of the Arctic Ocean, as well as coming through the Barents Sea. On the other side, through the Bering Strait, you have Pacific water. Both these water masses are warmer than Arctic source waters and are considered a nutrient source for it. So let's now look at this from the point of view of taking a cross-section across the Arctic. I'm going to flip this around so the Pacific's on the left side of the figure. So we're taking a cross-section approximately across the Arctic like this, and we get a schematic such as this that shows you where you get that warm Pacific inflow water quickly subducting below the surface mixed layer. And you have Atlantic origin inflow water on the eastern side. And you can see the Arctic is super layered, and there are multiple processes that we think are responsible for driving mixing within the Arctic Ocean and able then to flood heat, salt, nutrients from these deeper water masses up to the surface. Now, why do we need them? Well, because of course, in the context of primary productivity, that's only happening up here in the sunlit euphotic zone. And the spring blooms quickly exhaust any kind of nutrient supply that's been accumulated over the winter. Right, so what did we know before we started? Well, in the IPY-ESBO project, we took some measurements along the kind of perimeter of the Arctic of temperature, salinity, and also turbulence. And as Paul Abrahamson reminded me yesterday, yes, it was 16 years ago that we went to sea together. But anyway, and we looked the same as ever, I tell you, for sure. So, what did we find? Well, what we found is that we had sections across here, here, and here. It's really hard to not shake. I think it's because I'm getting slightly less young. Okay, so, and what we have is these group of red profiles, and this is temperature, and this is salinity. This group of red profiles is taken to the west, and then the green profiles further along as you go along this boundary current, and the blue profiles farthest to the east. So example profiles here are west to east and west to east. And you can see that this kind of subsurface Atlantic water, which is much warmer than the surface waters, tend to be cooling as you go towards the west. It's losing heat, and we postulate the heat must be lost to the surface. But if you do a close-up of both the temperature and salinity profiles, what you see are these characteristic staircases in both temperature and salinity, which are indicative that double diffusive convection is occurring. This is a very slow mixing process that depends on the differing molecular diffusion rates of heat and salt. So if you have a warm, salty layer below, like we have here, underneath a fresh, cold layer, the heat diffuses across the interface quicker, and then this raises the temperature of the water next to the interface that can then convect away from the interface. Conversely, it leaves behind the salt, which then increases the density of the water just below the interface, and that convects away as well, reinforcing these little interfaces that we see, these kind of step interfaces. So this process is pretty slow, and what we found is that if you compute the heat fluxes through these steps, they were an order of magnitude too small to account for the total heat content difference between these different sections. So this reinforced the notion that we had previously that the sea ice in the central Arctic really was making the Arctic Ocean a very quiescent basin, not much mixing happening, and that any sorts of processes that can account for this difference are probably happening on the shelves, and so we need to have exchange with the shelves to drive this cooling And we obviously assume that the shelves are much more dynamic places in which we get more mixing. More about that later, but the idea that the Arctic, Central Arctic was quiescent was reinforced by this bit of work by Don Perovich. 2007, of course, was the first record minimum sea ice extent year. And what he found was that it really was down to the ice albedo effect. As the sea ice was lost, the heat, the solar input to the ocean, so the heat uptake by the ocean, far exceeded the heat required to continue the basal melting. So really seasonal heat release and storage and release was sufficient to explain sea ice losses in the noughties, as it were. And so there we go, seasonal storage and release within the mixed layer. And then you might ask, and double diffusion happening all around the central Arctic basins, and then you might ask, okay, what about wind-driven mixing? What's happening here? Well, wind-driven mixing, of course, happens everywhere where there's ice, but more so where there's no ice. And in 2012, Bangor again was privileged to go out and make some measurements, turbulence measurements here in the Beaufort Gyre. And what we found is that they were at sea during what was called the Great Arctic Cyclone. So these are winds, and here is ice. So the yellow is the ice concentration, and the gray is the draft. So you can see that these big winds were happening at a time when there was very little ice or no ice. And currents from a mooring showed that there really was the big input into the kinetic energy of those currents, and there was kind of differences in the currents across the mixed layer base when you compared the currents in the blue layer to the currents in the green layer. There really was a difference in them. And if you expect that shear is driving turbulence, which is what we expect to be happening, what we found was that actually when you measured the turbulence, and the measurements of the turbulence are here in the dots for both the Pacific water and Atlantic water layer, they really didn't correspond to when we saw big shear, which is the gray. So what we were concluding from this is that in the central basins, as the ice has melted, that the mixing, despite being able to put lots of energy into it from the wind, is suppressed by the layering of the ocean. The extra fresh meltwater in the central Arctic basins is creating really stable stratification. So even the extra energy wasn't doing anything to necessarily mix the warm water up. And then you say to me, okay, but you talk to me a little bit about the kind of mixing on the edges of the basin earlier, saying that we need mixing on the shelves and the slopes, maybe. That could be important. Well, what we were able to show way back at the, say from observations mainly made in the noughties, I would say, is that turbulent dissipation does seem to match the amount of energy put into the ocean from the tides as you go around the basin. So on the slopes themselves, we do think that the tides have an influence on the mixing. And you say to me, okay, well, this is not new. Other oceans have this too, and you would be correct. However, in the lower latitude oceans, a lot of the energy coming out of the tide, and so by energy coming out of the tide, we normally mean, say, in a stratified ocean with different density layers, as the tide passes over some seamount or continental slope, if it goes this way, it draws the isopycnals down, and this kind of fluctuation, disturbances in the density layers, propagates as an internal wave, taking the energy away from the slope. However, because of local rotation, above 74.5 north and south, the M2, or the semi-diurnal tide, which is the biggest source of tidal energy, tends to not be able to be propagated away, but rather trapped. So if the energy comes out of the tide into an internal wave system, it can't propagate away, and the energy, instead of going into linear propagating internal waves, is trapped at the feature where it was generated. And as it is trapped, it is also nonlinear, it's high frequency, unstable, and susceptible to breaking right at the location of its generation. And so circumstantially, we have a little bit of evidence of this possibly happening here north of Fram Strait. Results from Ilkefir show that actually the diurnal tide in this location was drawing the isopycnals down. You can see the tide goes up, the isopycnals get drawn down, and this at the same time coincided with the Froude number, or the hydraulic condition of the ocean at this place, being higher than 1, which is critical for the generation of nonlinear waves. So if you get Froude numbers above 1, you can get these nonlinear waves generated. And just so it happens, they were also able to make turbulence measurements that show these red here in the number 4 is really an indication of these Lee waves dissipating right where they're generated. So in other words, Antarctic tides do generate nonlinear Lee waves that can drive mixing around the boundaries. Now, actually, the process that I've talked to you about doesn't depend on the tides. This generation of nonlinear Lee waves just requires any type of current that can push down the isopycnals as it's coming off the slopes. And so we actually saw during Peanuts a really interesting thing where we had from a mooring here just off the Laptev Sea, there were big downslope currents or off-slope currents at the same time as which we had depressions in the isopycnals. Turbulence measurements made at this time period in the red here showed you that the turbulence observed at this time was much, much higher than background rates for this location. What is the consequence of this for the nutrients? Well, I'll tell you in a minute, but first let me explain to you what we think are driving the big downslope currents. We actually think that this may be a sign of what are known as continental shelf waves. So if you have a storm anywhere, it's a low pressure. It sucks up the sea level, which creates kind of this blip in sea level, sea surface height. And this blip propagates away from its generation point as, if it's on the continental shelf waves. And as it reaches, this is a simulation by Seth Danielson. Oh, let's go back. I keep pressing the wrong button. As the storm, as this kind of continental shelf wave spreads over the continental shelf, and as it approaches the coast of the continental slope, as it were, you can get the generation of big off-slope currents. And so this is what we think was explaining what was happening at that mooring in just offshore of the Laptev Sea, because we did not observe a storm occurring right at the same time in that location. So we really think that these continental shelf waves are big propagating systems that come from storms occurring somewhere else, days before on the continental slope. So that's really an interesting prospect to think that there's wind-driven mixing occurring remotely to where the storm is, necessarily on the continental slope. And so, as I said, let me promise to tell you what the nitrate flux was. The nitrate flux was 1,600% more than the background rates for that single event. We also did see enhanced primary productivity at the same time, or at least enhanced chlorophyll A. And what we believe is that these events, so using the mooring data, Kiki then identified the events from both large off-slope currents and depressions in the isopycnals, and these are all indicated here as asterisks on these lines, and they're plotted on top of a line that shows you sea surface ice extent, or ice concentrations for this mooring. And you can see that we get more events when the ice is absent than when the ice is present, even though I will say we also get events during the ice, when the ice is present. So as we lose the sea ice, what we think is that these types of mixing events are going to increase in frequency in future. At the same time, the Arctic Ocean is changing in other ways. We have seen, again at this mooring here, this is the depth of the top of that Atlantic water layer. Over time, it has been coming closer and closer to the surface. This is a signature of what we are now calling the Atlantification of the Eastern Arctic. And it's really driven by the fact that the Atlantic water inflow has also at the same time been increasing in temperature. The impact of this on sea ice in the Barents Sea, for instance, so here you've got the seasonal growth and retreat of sea ice. And once we got past about 2005, the sea ice was no longer growing past what turns out to be the polar front in the Barents Sea. It was staying north of the polar front, and that continues to be true today with the Barents Sea, Central and South Barents Sea being mainly sea ice free these days. Okay, so if we take these two things into account, higher fluxes from more wind-driven events and Atlantification of the Eastern Arctic, and put them together, I think we expect higher fluxes overall. So the Atlantification suggests those background rates will move towards the east, and so at any particular location, you're going to get higher background fluxes as well. I should say, of course, for the biogeochemists in the room, we do know that there is also a long-term decline in nitrates within the Arctic and nitrate supply. So the question for the future is the enhanced mixing going to compensate for the long-term decline, or which is going to win out in terms of primary productivity? So those are really important continuing questions for us. But one thing we can say is that on the shelves themselves, which are more and more sea ice free over time, this is work from an MSc student who computed the potential energy anomaly for the LabTEF-C, and this really is just, think of it as a metric for stratification. And the difference between June and October stratification tells you how much energy has been put into mixing that continental shelf system. And you can see that this really is the first sort of indication that we're really getting summer mixing increasing in the LabTEF-C over time. Which is exciting to us because actually it's been really hard to show that mixing is increasing in the Arctic, though we expect it to be. Right, so I've talked to you a little bit about tidal mixing, exciting new wind-driven mixing processes, which drive what we call internal wave breaking, and seasonal storage. How about these eddies? I mean, eddies are pretty cool, right? We all like eddies. Well, let's now take a mental break and watch a lovely video produced by my collaborators and colleagues who embarked on a voyage, the SODA ONR-funded program, out in the Western Arctic to look at Pacific inflow waters. My student Ben Barton joined them to take nitrate measurements on that cruise, and this is what we found. There was, during the cruise, a big filament of Pacific water showing up in sea surface temperature images as well as chlorophyll A images, and you can see that the measurements they took scanning through this filament show, again, that warm Pacific water which subducted below the cold surface waters. And in the density classes, which are indicated by the dark lines on this temperature salinity plot, in those density classes, you can see enhanced chlorophyll A, as well as, for nitrates, enhanced nitrates at the bottom of this plume. So what do we think is happening? Well, let's see if this works. Hooray! It's important, by the way, for science communication to have kind of high-profile words like heat bombs. Here's Ben. Here's Jen, who led the cruise, Jen McKinnon. looks like an alien, doesn't it? I always think that. So we think mixing is happening at the base of the plume, drawing nutrients into actually the nutrient depleted Pacific water. And then these, of course, can propagate into the central Arctic, where they release their heat and other contents slowly over time. Right, so you can go and look for that online if you want and watch the rest of that and the credits. But we think that's what's happening with that Pacific filament. Now, this is also some more excellent MSc work by Maddie, who is in the audience. I would point at her with the laser pointer, but that's not a good idea. And we wanted to know really, how do we join all these things up for peanuts, you know? Are we seeing more mixing driving nutrient fluxes that can sustain blooms past the spring bloom season? And so Maddie took, let's go back. Maddie took a 1D kind of mixed layer model to look at times at which we can see that mixing is driving nitrate fluxes up from the below the mixed layer into the euphotic zone, and we compared it to the primary productivity, net primary productivity from the biomass model for this location. And you can see that as the melt season begins, you get the spring bloom that doesn't depend on any kind of new nitrate infusions. But however, subsequent sorts of blooms do all seem to correspond to when you get nitrate injections into the surface layer. So this really does seem to suggest that the mixing is really important for sustaining the blooms past the first kind of the start of the melt season into summer and late fall. So what we then had is another MSc student. See, the Bangor MSc students are rather fantastic. So my most recent MSc student, Tom Davenport-Jones, has been supervised by Joe Hopkins and I on this project in which he has been looking at seeing whether wind mixing does indeed correspond, or wind input to the ocean does indeed correspond with higher NPP as derived from satellite products. And so what we're showing you on the top here, for the Barents Sea sector, you can see this kind of mean SST showing the warm water inflow of the Atlantic water, and on the Pacific side, the warm water inflow from the Pacific waters. At the same time, he's plotted kind of events that are more than 2 standard deviations above the mean for W3, or rather the wind speed cube, which is a metric for wind energy input into the oceans. And you can see these are what you get kind of longer durations, sort of aligning with where you get higher SSTs, as well as what is more striking, I think, is this more frequent kind of wind events occurring along the path of the warm SSTs. So effectively, what we think is that the Atlantic and Pacific warm inflow pathways correspond to longer lasting, more frequent wind events. What does this mean for MPP? So here's that picture of frequency of wind events, and here is the MPP events. And from the satellite data, I think it's really striking. What we were really amazed to see is that really there's a strong spatial correlation between these data sets. So this seems like good observational, circumstantial, I will say, evidence that the extra wind-driven mixing is certainly providing the nitrate fluxes that sustain the blooms in places like the Barents Sea and the Chukchi for longer than the spring bloom. What I will say is that the NPP product does not allow us, even though it's a daily product, it does not allow us to look at the evolution of NPP over the course of a single storm, because satellite net primary productivity depends on chlorophyll A measurements. These are obscured by clouds. You may have noticed that storms tend to associate with cloudy conditions. So in terms of being able to study a single event and seeing what is happening is really difficult to do with just satellite measurements alone. So the best we can do with these data sets are then to look at these sorts of spatial correlations of hotspots of both mixing and MPP. And, it really requires a more now, if this is really true, then maybe it's actually more frequent rather than longer lasting storms that matter to the net primary production. That really has consequences, as you all know, for both the phytoplankton community structures and which species are able to respond to that sort of forcing and sort of kind of frequent nutrient fluxes. Okay, so does mixing in the Arctic Ocean melt ice? Yes, we think so. And actually, we have, since the start of the 2020s, we do think that the Arctic Ocean processes are as important as the surface processes and the seasonal heat release. Winds and tides are both driving mixing in unusual for lower latitude ways that are currently underrepresented in models. And a really good example of this is from this giant storm reported in 2022 in January. It was a record Arctic cyclone in the Barents Sea. And to the north of the Barents Sea, they found that the sea ice loss was twice what the models expected. So it's a process that we think looks very much like that remote-driven wind forcing driven by continental shelf waves that is not at all represented in models at the minute. And of course, we think that all these processes will then continue and become more important in the future. But what I wanted to say to you is that it's not just people who are interested in the Arctic that should care about what's happening in the Arctic. I mean, hopefully I've already made the case that, our weather matters. It really matters what happens in the Arctic and the heat losses in the Arctic to our weather, but the Arctic has an influence on our weather in other ways as well. This is a result from a recent paper by Bob Marsh, and these are kind of particle trajectories coming. So Djern over here looked at all the particles coming south through this line and backtracked to their origin and look at the salinity differences along the back trajectories over this whole time period. So particles in these kind of CMIP, high-resolution climate models that provided the data for him to do this. And what you find is that, let's go back. Oh, sorry, pressing the wrong buttons. What you find is that this kind of freshening is really a signature of Arctic-sourced freshwater in the surface ocean of the subpolar North Atlantic becoming more important over the next few decades, whereas the subtropical source water doesn't make it so much into this sector of the subpolar North Atlantic. This has then got an impact on the stratification of the North Atlantic, which is kind of important. So remember I talked to you briefly about potential energy anomalies? Well, that's the type of analysis we used in this study. And what Bob has been able to show is that as we go into the future, and the colors represent going from now towards the future, is that the paradigm where the surface North Atlantic is TS compensated. And so for physical oceanographers, we know TS compensation means that you can have warm and salty, or otherwise known as spicy water, on the same density surface as cold and fresh water, otherwise known as minty. So this minty, spicy paradigm, we're going to be moving away from that over the next few decades. In fact, we're going to be moving to a warm and fresh paradigm. And we have called this warm and fresh kind of characteristic springy, because spring is warmer than winter, and spring and mountain spring is fresh. So we've gone for springy, And I know we haven't labeled it, but it's very clear that if you're going for cold and salty, that's going to be briny. So, so we think that the surface North Atlantic is going to be transitioning to springiness. This has consequences for that surface stratification. If you get a thinner mixed layer in the North Atlantic, it's going to warm up quicker in summer, cool down quicker in winter. So you get warm and cold anomalies at different times of the year. Marilena Altman's work has shown that this can then have an impact on storm tracks. So we're trying to draw all this together and write a paper about this for the Arctic Connect oceans portion of the work of the Arctic Connect project. So I guess I just wanted to say that what happens in the Arctic really matters to all of us, not just because of how it can influence weather in winter, but also how it can influence weather at all other times. Thank you very much, and here are my wonderful collaborators.